Welcome everybody to the Kent seminar. Today Erman Gungor is one of the PhD candidates. You're a candidate, right, Erman?
Not yet.
Not yet, but he's going to be soon, I am sure. And he's going to be talking about his TRD paper about the development of proposed overweight vehicle permit fee structure in Illinois. It's really great work. I'm sure you will enjoy the presentation. But just a little bit introduction for Erman, for those of you who don't know, or for those who are watching us on YouTube, is Erman is the pursuing his PhD. He's very much into data science, right, Erman? And then is under the supervision of Professor Erman Al-Kadi. And he finished his bachelor's degree in the best school in But I also finished my degree, but back then it wasn't that good, but it became even better in the recent years that produced students like Erman and again. So let's just give him a warm round of applause.
All right, good afternoon, everyone. Today I'm here to present a study whose title is Development of a Proposed Overweight Vehicle Permit Fee Structure in the State of Illinois. So I'll start with giving you guys a motivation of the study in a broad sense. You know, in one hand, we know that population has been increasing, and that the more people we have, the more goods we have to transport from point A to point B. That creates the increase in the truck traffic. And also FHWA is projecting that this truck traffic increasing is going to keep happening. We are going to keep having more people, and we are going to also need more trucks moving the goods from point A to point B. This is one group of facts. The other group of facts is that according to ASC infrastructure cards, our infrastructures are not doing really well. And plus, Department of Transportations are facing the challenge of developing maintenance and rehabilitation budgets, but still they are expected to provide well-maintained and functional infrastructure. This constantly increasing truck traffic. Therefore, they have become more interested in funding the research projects in the field of transportation infrastructure management that tries to address the issues, especially related to their revenue structure and systems. And the goal of today's presentation is addressing one of such issues in the infrastructure management, which is up-to-date assessment of impact of overweight vehicles on the highway system. Now I will give a quick overview about the overweight limits and how it works and so on. So intuitively, we know that we cannot keep loading the trucks, right? Almost all the countries in the world has the limits that for the waste that you can put on a truck. And in the United States, those limits are calculated by this formula, which is called federal formula, and it has been in use since 1974. As far as I know, other than 3 states in the United States are using this formula to calculate the weights for truck traveling in their borders. And there was a recent study came out 2 years ago. It was a national study, and they investigated the possible impacts of modifying these limits. Although they noted a couple of advantages of changing those limits, they didn't recommend any changes to existing limits. It means that for at least another decade or so, we will be calculating our weights based on this formula. But in my simulation, as you see, I was loading the truck block by block. It means that the load that's carried by this truck was divisible. But what if it is not, right? What if I carry a load that I cannot divide into smaller parts? Then I exceed the limit, and in that case, I have to buy a permit. So I want to mention that the limits, as I mentioned, set by the federal governments, whereas the development of fee is delegated to state governments. So it means that if I am carrying the weight more than limits, I have to go to state governments and get a permit so that I can travel through those states. So in the light of this overview, the objective of study was following. So Illinois has established a much more comprehensive overweight fee structure as compared to other states, because, for example, there are states that are just using the flat fee. You are just paying the fixed amount regardless how overweight you are. Whereas the permit fee used in Illinois was taking the gross vehicle weight, axle weight, and distance into calculations. But it was established in around 1982, as far as I know, and therefore most of its parts have not been revised more than 30 years. So objective of study was basically proposing a new the fee structure with the motivation of and with the objection of capturing the up-to-date and current economic impact caused by the overweight vehicles on highway systems, specifically for payments, bridges, and highway safety. So I hope so far I gave a clear image about the motivation and objective of the study. Now I'm going to start talking about the methodology that we follow. We follow fully data-driven approach for fee development because of its ability of making the decision more generalized as compared to mechanistical approaches. And as a natural first step of any data-driven framework, we collected a bunch of databases. We collected databases about the traffic, about the infrastructure conditions, about the crash databases, and so on. Later, we used the state-of-the-art prediction classification algorithms to develop models to predict a bunch of variables. For example, crash number, payment condition, bridge deck condition, and so on. Later, we used the prediction and classification algorithms to develop 3 individual fees: bridge fee, payment fee, and safety fee. And then we combined all these individual fees into one final fee, and that was our end product. So I think it's a good time for me to take a moment and give a little bit of more information about the project and acknowledge my co-author. So this project was completed in last summer, was funded by IDAT and managed by, here he is the permit unit chief, and just a man, also he helped us a lot from IDAT. The principal investigator of this project was Professor Erman. He managed the entire process of developing individual fee. Additionally, he was extensively involved in the bridge fee development because I was the PhD student who was working on that part. The payment fee was developed by Professor Hao Wang from Rutgers University and one of his students, Jingzhang Zhao. And the safety fee was developed by Professor Oyang from YUC and one of his students called Antoine Petit. So honestly, all these individual fee development deserves an hour-long presentation, but obviously I cannot do it. So I will try to summarize the development of all these individual fees and how we put them together by trying to highlight the important points behind all, each individual fees. I'll start with the bridge damage cost analysis, or bridge fee. And this is the framework that we are following for the bridge fee development. We are using 2 different databases, National Bridge Inventory, NBI, and the wave motion data. From National Bridge Inventory, we are obtaining the variable regarding the bridge characteristics, such as the age of the bridge, location of the bridge, and so on. But NBI doesn't have any information regarding the applied load. So for this information, we had to go and use another database, which is wave motion data, to get the load information. Later, we insert those variables to a machine learning algorithm or artificial intelligence algorithm, whatever you want to call it, to predict the deck conditions with respect to those variables. Later, we use these machine learning algorithms under 2 scenarios, with and without damaging trucks. And as one may expect, these 2 scenarios are producing different service lives, right? One, for example, let's say 40, the other one 48 years. Then the next step was quantifying this difference in the service life in terms of cost. And the link was conducting bridge life cycle cost analysis, which is giving us the final fee. Now I'm going to introduce the National Bridge Inventory. That's the online database maintained by FHWA. It's publicly available. That has many variables regarding the bridge characteristics, like age, the latitude, longitude, and so on. Also, it has a variable regarding the condition of the bridge in terms of 3 bridge parts: deck, superstructure, and substructure. Condition data is coming from the manual inspections. It means that an engineer goes to a bridge and follows a guideline and grades a bridge, changing from 0 to 9, 9 being excellent, 0 being failure. So in this study, we are focusing on the predicting deck condition, as everyone else doing in the literature, because it has been reported in the literature that the deck is the part of the bridge that deteriorates faster as compared to other parts. The second important point about our framework was vehicle weight distribution and estimation of this distribution over the network. So this is the map of Illinois. These green crosses shows the location of the wave motion station that we had the data from. And if you have the data and if you do simple operations, you can easily extract this gross weight distribution over the weigh motion stations. But the challenge was here that we don't have this information on all the bridges over the network. I have like we had around 20 weigh motion stations, but there are thousands of bridges distributed over the network. So the goal was kind of interpolating or estimating the similar distribution for all the bridges distributed over the network. And the solution that we came up with using kernel smoothing or Gaussian mixture the models or the non-parametric bump models combined with the lasso. This algorithm, this approach enabled us to approximate this curve for all the bridges over the network. The next step was the variable selection. So we had around 120 variables from MBI, and we had more variables coming from the weigh motion data. We had to do some kind of variable selection because we cannot insert all these variables to machine learning algorithms because it's going to do overfitting, high variance, and the low testing accuracy. So for this variable selection, we used the algorithm called stepwise forward regression. And at the end of the day, this is what we had. We had this simple input-output model. We had the selected inputs. We put those inputs into a machine learning algorithm called support vector machine that I will explain soon. And then we were predicting the deck conditions. Quick introduction for support vector machines is that one of the most commonly used and popular machine learning algorithms in the literature. What it does in a very simple sense, it creates this linear hyperplane by solving this optimization algorithm. It works perfectly if your data is linearly separable, but we all know that the linearity is not a very realistic assumption for the real-life problem. And the way that SVM handles nonlinear data is using what they call kernel trick. What this kernel trick does is it maps the data into higher space with the hope that the data is going to be more linearly separable. And this situation is demonstrated here. This is my original space. I have the data in two-dimensional space, and there is no way that I can separate this data with a linear line. But if I map this data into higher dimension, then I can fit a linear hyperplane to separate the data and classify the points that I want to classify. Again, like this is a very broad concept. I just wanted to summarize it as quickly as possible. So we did some data processing. We did two steps for data processing. One was mapping the data. So we mapped this condition data into three categories: good, medium, and poor. And the motivation behind the mapping was high subjectivity in the MBI data, because as I mentioned before, those condition data is coming from the manual inspection, and they are very subjective. An engineer can give a 9 to a bridge, and other engineer can go and give 8 to the same bridge. So in order to eliminate this subjectivity and increase the performance of our framework, we did this mapping. But this mapping created some imbalanced data problem. As you see, I have three categories with imbalance the distribution. So the imbalanced data set problem is very important when you are doing any kind of work related to data science, and you should address it. You can find many papers about this problem. And in this work, we are using what's called random undersampling to address this problem. What we are doing, we are going and randomly drawing around 5,000 samples from each category. At the end of the day, we are having the data set which is balanced. After this, we followed the very conventional machine learning framework. We divided our data set into testing and training. Then we divide our training into validation and the training. And we compute the accuracy. And our accuracy, in average, was 75%, which is quite comparable to the values that are reported in the literature. So far, I didn't use any word of overweight fee. Nothing. I just introduced the machine learning models that we developed to predict the deck condition. Now I'm going to start talking how we are using this model for fee computation, and the link between these two is the scenario development. So for this scenario development, we have to add one more variable from MBI, which is called inventory rating. which is defined as the rating will result in a load level which can safely utilize an existing structure for an indefinite period of time. So what it means, if I apply a load on a bridge that is below this limit, that bridge should sustain that load for the indefinite period of time. So in a way, it serves like a fatigue limit. So we are kind of leveraging that variable that's currently available in MBI for our favor, and we are developing a new variable that we call damage load, the difference between the applied load and the inventory rating of a bridge. Under this variable, we are developing two scenarios. One is the actual case that we use the actual traffic that we obtained from wave motion data that includes the damaging trucks and loads. In the second scenario, we are removing the damaging load, and we are trying to quantify the difference between these two scenarios. Here, in theory, by the definition, if you remove the damaging load, your bridge should last forever, right? But our machine learning algorithm, when you increase the age, it finds that even these bridges without any damaging load are failing. So it means that we are implicitly, considering the environmental impacts on the bridge condition. The second thing that I'm going to talk about now, I will try to demonstrate or illustrate the framework that we developed on one bridge. So this is the first step. I collected all these variables from MBI, and I put them into my machine learning algorithms, and apart from the age. So with age, what I do is I put age as a 1 year. I predict deck condition. Then I increase age by 1, and I predict another deck condition. So I keep increasing the age of the bridge until the predicted deck conditions become 4 or lower, which is defined as the failure limit for deck. So by following this framework, I calculate the service life of a bridge. Then I go to second step, which is the hypothetical case, and I follow these 3 steps. First, I extract the inventory rating of a bridge from MBI. Then I normalize the x-axis here. So before it was the gross weight of the vehicles, now they are ratio. So ratios more than 1 means that I am applying a load on a bridge that is higher than the inventory rating, which means that they are reducing the fatigue life of the bridges. So I label those trucks in that category as a damaging trucks. And for the hypothetical case, I convert them into non-damaging trucks, right? And when I'm doing this, I want to make sure that the amount of goods being carried on a bridge stays the same, which means that if I apply the number of trucks with the expected load, they are going to be the same. And this is illustrated in this situation. For example, in the actual case, I have 250 trucks, and in the hypothetical case, I have 298 trucks. What I did, I just converted bigger trucks into smaller trucks so that they are going to be below the inventory rating of the bridge. And I have the new sets of inputs, and I calculate the service life by repeating the same procedure. The next step is very easy. I just want to quantify the difference between these two scenarios in terms of cost. And we conducted a bridge life cycle cost assessment. IDOT provided us with very detailed report for us to extract this information. What's the cost of new construction? What's the cost of deck replacement, and so on. And then we calculated equivalent uniform annual cost using this formulation. It is essentially a function that takes the service life of the bridge as an input, and it returns to the uniform annual cost. So we put the 40 and 45 as an input to this EUAC. It gives the cost difference between these two scenarios. Then we calculate the damaging load, and then finally we were able to calculate the damage cost as a function of load and the area. So that was the example on one bridge. We took that example and applied all the bridges in the state of Illinois, and these are the statistics. So what is the missing part here is that my cost is still not function of miles. So still I need the information to convert that cost into a fee by integrating the miles. And the way that we do it, adding extra information to our cost. What are those extra informations? For first, number of bridges, then the center line mileage, which enabled us to compute the bridge per mile. And then also IDOT provided us with the average deck area in the state of Illinois. So if we multiply these values with the mean cost here, we can compute the final bridge cost for overweight vehicles. So I hope I am not very fast. I have a lot to cover, so I'm trying to go as fast, also as explanatory as possible. And now I'm going to start talking about the payment, the damage and cost analysis, and how we develop the payment fee. So this is the framework that we follow for payment fee development. We collected 3 different databases: payment condition, climatic data, and truck traffic. And then we developed the payment performance model. And then we conducted the payment SCCA as we did in the bridge part. And in order to add the mile information to our fee, we use the permit database that is also provided by IDAT to extract the vehicles that are traveled by overweight vehicles. And finally, we calculate the payment damage cost. Payment performance model started with doing some explanatory variable analysis like we did in the bridge part. And the goal was identify the variables that's going to help us to predict the changes in condition rating system. And we tried a couple of other, couple of forms to develop the regression equation. And we found out that this equation is the one that gave us the higher accuracy. So in order to increase the performance of the regression equations, we grouped our data into 4 based on the surface type and based on the highway type. For example, asphalt, concrete, interstate, concrete, interstate, asphalt, concrete, non-interstate, and concrete, non-interstate. And for each group, we developed a regression algorithm, and the results are given in this table. And we have good accuracy. The second step was conducting life cycle cost analysis. We basically follow the IDAT guideline for payment SCCA. IDAT gives the regular maintenance activities for each surface type and with their corresponding cost. So we gathered all this information, and we did the basic payment SCCA. And then we needed the information about how far those overweight vehicles are traveling through the states. And we extract that information from permit database to get the vehicles miles traveled by overweight vehicles. And finally, this is our final step. We computed payment damage cost for each road type, for each surface type, and with changing traffic levels. But we were expected to report one final equation. So what we did, we did some statistical assumptions, and we take the weighted average of those costs that I just showed. And this is our final payment damage cost. So in order to convert this cost into a fee, we have to compute the delta easels, which is defined like this. Basically, we are removing the excess weight on the axles of overweight vehicles from the legal scenario that we are defining. And this is how we compute the final payment fee. So now I'm going to start talking about the safety cost quantification, which is the final part of the fee. So these safety performance functions are the essential part of the safety cost. Basically, many people are developing those functions, safety performance function, that links the variable in the traffic, such as AADT or the length of the road and so on, to the expected yearly number of crashes. So we adapted one of those functions to our study by adding the term of overweight trucks. And once you have it, actually, once you have this equation, rest of the work becomes much easier. But in order to get this equation, you need to have 2 more variables, which is the expected yearly number of crashes. And the second one is the overweight traffic on each road segment. So for the first variable, I will explain how we obtain it. But before I go there, similar to what we did for the payment part, for this part also we group the data so that we can increase the accuracy of these regression algorithms. So for the mu, the expected number of crashes, we basically fit negative binomial regression to our crash database. And once you fit using the maximum likelihood, and once you fit it, you can easily have these mu for each subcategory of the data. For the overweight traffic, we need to model the traffic flow as a mathematical equation because of the fact that we just have the traffic composition at the weighing motion stations. That is demonstrated here in this plot. For example, let's say this 1 and 2 shows the location of my weighing motion stations. For in that locations, I know how many overweight truck I have. I know all the truck composition. But what I don't know how the truck compositions are changing over the highway network. And in order to get these unknown truck compositions, we model the entire traffic as a mathematical model so that we will be able to estimate the truck compositions on each road segment on the network. This is just a snapshot of the model. I'm not going to go into details, but I will just say that what it does, basically, it generates truck traffic composition on each road segment. And there are two things that this model is making sure. One is that our generated truck composition is matching with the data at weighing motion stations. And the second, that our generated truck composition is compatible with the permit database that we were provided with. And this is the last step to get these regression coefficients in the safety performance function. You can do it easily using any kind of the library. So finally, for example, we were able to obtain one safety performance function. As you remember, I said we were grouping the data into 4 categories. And for example, this equation illustrates the one safety performance function that we obtained for one category. And once you have this equation, what you are interested in, what is the effect of this variable on the expected number of crashes? And the way that we are answering this question is basically taking the derivative of this equation with respect to this variable. And then it gives us this long equation. And once we integrate once we put the traffic and the length information in that equation, we were able to finalize the safety cost. Again, this was only for one category. If I do the similar step for all the categories that I explained before, I get this table. And if I take the weighted average of this table with respect to the length of each road, each category, this is my final safety cost. So this slide doesn't say anything new. It just puts all the equations developed together, and it also combines into one final permit fee. So once we were developing, so these equations was developed, as I mentioned, based on taking the average and doing some statistical assumptions. So we also proposing some kind of innovative way of issuing a permit using this framework, because IDAT is already using the online system for truck owners and drivers. Basically, they go this online system, they put their origin and destination, and IDAT provides them with the route and the permit fee. So we say that let's leverage this existing system already, and when they put the origin and destination, we can extract how many bridges those trucks are going to pass over with their load carrying capacity. What is the road type? They are going to travel over the asphalt concrete or the Portland cement concrete. We are saying we can extract all this route specific information, insert our framework so that we can compute the payment, the permit fee in more accurate and fairer way. So we expect that this is going to bring 2 advantages. One is we are going to avoid over or undercharging. And the second is it's going to allow us smart revenue allocation, because we are going to know which bridges. Actually, this idea was proposed by Gino Kohler. We are going to know which roads is getting deteriorated, more, or which bridges needs more rehabilitation budget, and so on. So this is the acknowledgement. I just want to thank Gino for providing valuable, feedback to us throughout the study, so that we can, make not only theoretically solid work, but also practical and functional. And also, we collaborated with Rutgers University through Professor Hao Wang. So that was all I had to say. If you have any questions, let me know. Yeah.
You were talking about a balanced sampling, and I did not understand why you want a balanced sampling when you don't have a balance in the original data.
Let me go. So if you feed this imbalanced data set into machine learning, what it does, because what machine learning does is, trying to represent this data by minimizing the error. So error, if you feed this data as it is, then it's going to learn how to minimize the error in these dominant classes. It's going to learn them very well, how to, but it's not going to learn anything because machine learning algorithm is not something magical, right? So you have to balance the data set so that you can avoid the bias in your machine learning algorithm. Yes, Professor.
One question, Erman. It looks like you have three different types of modeling efforts going on in this study, and they're not really following similar methodology. You took on machine learning, whereas in the payment condition you use different types of paper, but they're all more or less predicting the performance of an infrastructure. Well, what do you think about this inconsistency between the modeling approaches? Would that really affect your final outcome, the accuracy of your final outcome?
I mean, I don't think so, because at the end of the day, you can use any kind of algorithm as long as you have a good accuracy in the models. So in payment part, they were able to, for bridge part, because of the high subjectivity of the data, I think fitting a linear equation was not enough. That's why we had to go with more complicated, more powerful tools like machine learning algorithms. But whereas I think for the payment part, they were able to get a good accuracy by just using specific, linear model. So I think it just depends. As long as you get a good prediction model, good testing accuracy, the tool that you are using, I think is not important.
The same issue that you tackled with the bridges is existing for the payment. It's not really easy to come up with a good prediction model. I see that the payment groups are very simplified for Illinois roadways.
Yeah.
There are many more types of payment surface in Illinois that may not be really categorized as just XC and PCC.
Yeah.
The accuracy issues may exist actually in all of the other data sets.
If we group the data in, yeah.
Look at the characterization of the payment surface types in Illinois, and they predict the payment surface, payment conditions, not for the key structure. There are certainly for each interstate and non-interstate group more than 10 surface types.
Okay. So maybe I should email Professor Hao Wang and ask him why they decided to go with 4 category with respect to, but maybe they didn't have enough data points or.
So that's what I'm saying. If you see this now, when you open the box now,
Yeah.
data issues, collecting data, especially from payment infrastructure, there's always an issue of uncertainty, unknown.
Yeah.
That's why I was asking if you apply the same machine learning techniques to the other infrastructure groups like payments, safety, if you have expected different outcomes.
I mean, yes.
Would this improve your, let's say, final outcome when you're evaluating?
I mean, so in data science in general, there is a maximum error bound, and you are not expected to, minimize this maximum error. So the question is actually can be formulated if with the linear model that we develop in the payment, we are approaching this maximum error. We can. That's the actual question. So that's something that I need to check with. Yeah. So maybe we have to check. I mean.
We've already talked about that.
So I don't know why, maybe I should have been more involved in the payment fee development in terms of data science, but I don't know why they decided to go with 4 groups. But maybe limitation of data points and this kind of things might be the reasons. Thank you.
Thanks again. Good presentation. My question was, looking at some of your functions and the final equations that come up with
from regression or statistical analysis. One of the important variables, I think, is the overweight function, right? The overweight variable, rather.
In the safety part?
Yeah.
Okay.
And that, from both the safety and also the damage, the worst damage accumulation, maybe the extremes of the overweight condition would be really more detrimental if you just come up with from the data like an average value for that to pull into your series of equations. You may be missing the extreme ends of the damage and safety concerns too in this approach. So that's the kind of thing that sounded to me or looked to me like maybe the extremes are ignored. Do you have any answer to that?
Yeah, that's a really good point. And so, like obviously, when you average things, that you lose the information from extreme. So for this one, we are actually, I don't know how, if it's going to be applied or not, but we are, proposing this framework where there is no, averaging. So we are saying that for every truck and for every route, by extracting the bridge type, the road type, the ACE, like without doing any averaging, we are planning to, the compute the fee. I don't know how realistic to get this implemented in the real life, but this like as an alternative, because as you said, as long as we keep averaging the stuff, like all the people doing, we are gonna lose the information about the extreme.
Right.
Yeah.
But you're not doing averaging there?
I mean, so far this is a little like policy implementation issue. So if they want to go with the one formula like this, then we have to average them. Because if we were asked to provide a formula, but if we were asked to go with the more, with this framework, then we don't have to average.
Regarding the safety, and even with the ideal implementation where it becomes more localized and not like an average value, how do you justify charging, say, a fleet of trucks that are more safe than the ones that are actually putting in the data points for the safety or the crashes itself? So there's truck A didn't get into an accident ever.
Okay.
He will still be charged that crash fee versus truck B who has gotten into an accident. So how do you justify charging a truck that has never gotten into an accident with that safety?
That's a really good question. So underlying assumption is that when you increase the weight and the size of the trucks, they are going to become more likely to get involved in a crash. So it's not really the historical records. It's like about predicting future, how likely that truck is going to be involved in a crash. So this is the assumption that we are basing entire our work on. For example, if did you understand what I?
It's just because for the cost of the bridge, right? Those the condition of the bridge and the pavement is driven by the truck passing it, so it's more justifiable to charge.
Yeah.
But then when it's safety, there's
Yeah.
ambiguity of, okay, yeah, you should be charged this fee.
No, that's a really good point. And this is for example, again, like national study came like 2 years ago about changing the modification. Also, one of the points that they made, like we don't have enough data to assume that there is a direct link between the weight and size of the truck versus how likely they are going to be involved in a crash. But this is the assumption that we are doing like everyone else. Even that study, they did that assumption. And frankly, this assumption seems quite logical to me, that if you increase the weight and size of the trucks, it's going to become more likely to get involved in a crash. But there is a definite, because when they report the crashes on the traffic, they don't report the weight and the size of the truck. So we don't have the data really to reinforce our assumptions. Professor Oza?
Yeah. We have time, so we can.
Okay, sure.
Good discussion.
No,
So I have a big
really
picture
appreciate
question for you. You're a big fan of data science, right?
Yeah.
But do you see a future of, let's say, data science fusing with the mechanistic models? Because those bridges, payments, they respond based on their structure, right? They have some fundamental elements of how they respond to loading, climatic conditions. Do you think that everything can be done with just basic data science? But for especially for infrastructure modeling, should we really think about some kind of a hybrid modeling approach with the data science and some elements of mechanistic modeling?
No, that's definitely the way to go. I mean, I believe that if we collect enough data, we can be more accurate at predicting the performance of infrastructures as compared to mechanistical model. But what is the limitation about the data-driven model? What's going to happen in the future? For example, what happened with H293? It's basically a data science model, right? Then we had the white-based tire. Then how to say, like when we are developing let me put it in that way. The limitation of data-driven modeling is that it should be a data so that you can model your variable. So for example, let's say I developed this data science model for bridge condition development. But what if 2 years ago we have the totally new track with a new configuration? There is no way that my data model can simulate the situation because there was no data in my training set, right? So in order to simulate these cases that doesn't exist currently in today situation, we need the mechanistical part. So I think the best way is hybriding these two. What is the, for example, for feed development, there were a couple of other studies that used the mechanistical models, and they basically took the bridge and they modeled it using finite element models. But what is the disadvantages of this? Because of the high computational cost, they modeled like, I don't know, 10 or 20 bridges out of thousands. So they introduce bias into their decision-making process. And this is not just my only opinion. I think the National Science and Academy of Engineering made a review about that study. And they also said that if you do this, your analysis based on the bridge selection, payment selection, you introduce bias to your decision-making and entire formula. Whereas in our work, we were able to consider all these bridges and all these payment types and everything because we were following a data-driven approach. I don't know if I was clear.
Any more questions for Erman? Let's just give him another round of applause.
Thank you.